this video, I want to talk about the issue of damped forced vibration. So previously we've talked about forced vibration without damping, and really the only difference here is we're adding a dashpot into our model for our dynamic system. So let's go ahead and take a look at what that means. So here on the screen I have a drawing of a mass spring damper system, and it looks very similar to what we would have seen with damped viscous or viscous damped vibration. The only main difference now being, again, that instead of the weight providing a static force, or this force being static, maybe as a comparison, we're going to say that this force that is applied to our mass is varying, and it has some sort of sinusoidal function, so such that it's forcing an input to the system. So if I pull my mass out and draw a free body diagram, I might have the weight and the normal force, which I'm not going to really worry about right now. I have my applied force, and then I have my force due to the spring and my force due to the dashpot. So recall that spring force is dependent on change in position x and some spring constant k, and the force from the dashpot is due to the dampening coefficient c, as well as the velocity of x, so x dot. So similar to before, if we were to write a differential equation for this situation, we would have mx double dot plus cx dot plus kx. But now, rather than being equal to 0, as it would in free damped vibration, we have the forced input that shows up there. So this is probably the most general form solution that we might have for these types of vibrations, in that we have the applied force, we have the spring, and we have the dashpot all involved at the same time. And all of our other versions that we've looked at for vibration so far would be simplifications of this approach, in that different things cancel out depending on whether we're talking about non-damped vibration or free vibration rather than forced. So this kind of takes into account pretty much everything. So much like in forced vibration without dampening, we have both a transient and a steady state component to the solution to this differential equation. And the transient part we're not going to worry about because the dampening will cause that to go away. And instead then we're going to focus only on the steady state. And as a result, we get an equation for x, or a solution for x, that looks something like this. And we have two constants in here, a, which is just a constant giving us an amplitude, and we have phi, which is basically a phase lag. So it's how much the response in the position of the mass is going to lag behind the forced input, so the frequency lag there. So the equations that represent then a and phi are a little bit complicated, so it'll take a second to write those out. So you can see that these two equations are rather lengthy. It's never a good sign when you're drawing a division line that goes that long. And there's a couple of substitutions made in here that simplify a little bit the equations. So first you might note that we've got natural frequency in here, and that is defined as it has been all along, which is as the square root of k over m. And we've also got the critical dampening coefficient, which is defined as it was before as 2m omega n. So those two things haven't changed. We're still making use of those in the original definition. Now, what that gives us then is looking in this equation, we have a couple of things, a couple of ratios. One is the ratio of the forced input frequency to the natural frequency, and then we have the ratio of the dampening coefficient to the critical dampening coefficient. So both of those things are going to be useful in kind of evaluating, what's going on. So we often would know or be able to calculate this damp natural frequency, natural frequency omega sub n, and C over Cc is the dampening factor. So those two things are kind of common things that we might consider for a system. So like we saw before with forced vibration, we want to compute a magnification factor. And the magnification factor is basically the magnifier on the amplitude of the force. So if the force going into our system looks like this, then we want to know how is that getting magnified by the mass and the other components of our system, the spring and the dampener. So basically we need to pull out the denominator of our equation A. So I'm actually just going to copy that to save us a little time. And I'm only looking now for this rest of this term, so I'm going to take out the force. And therefore the magnification factor looks something like that. So now if we go ahead and plot what this looks like, I'm going to get a plot that looks something like this, where as before I'm plotting the ratio of the frequencies and I'm computing the magnification factor. Now I've done this then for a few different dampening factors as shown here. And what we see is that as the dampening coefficient approaches the critical dampening coefficient, which is where it is equal to 1, so the green line here, we see that we don't really get any magnification on it at all, right? Which is kind of what we would expect in that, it's critically damped, which means it's not going to oscillate as a result coming out. However, as that dampening factor gets smaller, so relative to the critical dampening factor, this ratio gets smaller, we start seeing again that high magnification on the amplitude of our output. So the dampener, in this case, if we compared this against forced vibration without the dampener, that dampener reduces that resonance-based magnification of the output amplitude. So we can kind of take that away by adding in the dampener. All right, so I will go ahead and stop there. Thanks.